got independent and dependent events. Ooh, I have a different color. There you go. Okay, so for independent events, that's what our I is. We've done it in red. The probability of event A and event B happening is simply the probability of event A times the probability of event B. In other words, saying that they're independent of each other, and no matter what happens for A, it does not affect the probability of B, and technically vice versa. Neither affect each other. Okay. For dependent events, probability of A and B happening is the probability of event A times the probability of event B given event A has occurred. Okay, and that's what this line is here. In other words, it's saying whatever the probability of B is, it actually changes the kind of depending on what happens with the probability of A. So we'll use kind of some classic examples. The first one we'll talk about is coins. Okay, a classic question might be flips. So what's the probability of getting 3 heads in a row? We know on a coin you either get heads or tails, right? So you get one or the other. Well, in order to get a heads, okay, so you get, if we made a factor tree, we have our heads, or probability tree, heads and tails, and they're 50% each, so you could say 0.5 and 0.5, okay? So once we get heads, does the probability of getting a heads the next time around change? Are we going to be less likely to get heads when we flip that same coin after?
No.
No, it's going to be the exact same. So because it's going to be the exact same all the way through, I'll do it one more time, heads, and you get a 0.5 chance again. Does that make it an independent or a dependent event?
I'm going to say independent.
That's right. It's independent because it doesn't matter what happened the flip before, right? It doesn't matter whatever happened the flip before. You still have the exact same probability moving forward when you flip the coin. Whether it's the same coin, a different coin, it doesn't really matter. The probability stays the same. Okay, so the probability of getting 3 heads, because we just discussed how it's the probability of event A times event B, and then we'll say event C. Well, that would be, let's say probability of A and B would be 0.5 or 50% times 0.5 times 0.5, so 0.5 cubed. So in order to solve that, let's do 0.5 to the power of 3, 0.125, that's what I thought. So probability of that event happening is 0.125 or 12.5%, getting 3 heads in a row. Okay, next thing, dice. For rolling a die. Okay, what's the probability of getting, we'll say 3 threes. I don't know why it took me so long. 3 threes in a row. Okay, so let's think about rolling a die. What's the probability of getting a 3? Do you know what it is?
1 in 6.
That's right. So to get a 3, we have a 1 in 6 chance. Okay. Now, because we roll a 3 the first time, does that affect our probability of our second roll? Does it change this probability?
No.
No. So what's the probability of getting a 3 again?
1 in 6.
Yep. And then that just keeps happening. Okay. Unless literally the sides of the dice are blowing up and we have less sides, they are very independent events. It does not matter what's happening. So we're looking at 1 over, and what's 6 times 36? 216. So 1 in 216, whatever that percentage is, would be the probability of getting 3 threes in a row, which means this is independent again. Okay. Let's talk about getting 3 kings in a row. Okay, from cards. Okay. Do you know how many kings are in a deck of cards?
4.
There's 4. And do you know how many cards are in a deck of cards?
52.
Yes, so we have a 4 in 52 chance of getting a king on our first one. Okay, so once I draw the king out, how many kings are left in the deck?
3.
3.
Yeah.
And let's say I drew a king the very first time. How many cards are left in the deck?
51.
51. Okay, so that's for drawing the next king. What about for the next king? How many kings are left in the deck?
2.
2. How many cards are left?
50.
Okay. Has the probability of each event stayed the same?
No.
No. It's changed. So which means what type of an event is this?
Dependent.
This is a dependent event. Now, we'll quickly calculate this here. 4 by 3 is 12, by 2 is 24 in, and we'll do 50 times 51 times 52. 132,600. So 132,600. So the probability is super rare that you get 3 kings in a row here. Okay, so that's how you calculate it. You just obviously the probability of the next event, so that would be event B, is switch changed given A, right? Now, I could make cards independent. If I draw the king and then, so imagine we have our deck of cards and we pull out our king, okay? If I take that king and put it back into the deck, then the probability then again is the same. It would be a 4 in 52 chance. But let's assume I'm drawing, and they usually say it with no replacement, okay? And I probably should have wrote that. We'll say no replacement. So because there's no replacement, the probability changes every time. And that's essentially the gist of the idea of an independent and a dependent event. Does one affect the other, okay? And those are the formulas to calculate it. You probably have 1 times probability of the other. And if they're dependent, probability of 1, and then probability of the other given that something has changed its original probability, okay?